So, in this lecture we will learn about two things. One is about bipartite graphs, the second thing is about minimal spanning trees. These are the concepts that we are going to learn in this lecture. So, let us first define what are bipartite graphs. Okay. In the previous lecture we talked about coloring or coloring the vertices of a graph. Graphs which can be colored using two colors, which can be vertex colored using two colors, are referred to as bipartite graph. So, let us write down the definition. Two colorable graphs are called bipartite graphs. Okay, so, if you have any graph and it can be colored using two colors, these are called as bipartite graphs. And the reason why they are called bipartite graph is because this naturally splits into two parts. Okay. So, let us say these are all the vertices getting one color. So, let us call it as color 1, and these are all the vertices getting color 2. Now, if you look at the edges of the graph, every edge is of this kind. One end is in this particular set, let us call this as A and this is B, and the other edge will be in B. Okay. This is how every bipartite graph would look like. One edge in one part and the other edge in the other part, because if you had two vertices in the same part, then of course these were the colors given to the graphs, and if you had an edge in which both vertices were on one side, then that would essentially mean that that edge is not properly colored, its endpoints received the same color. So, that is not allowed. So, bipartite graphs are essentially two colorable graphs. Now, we will give an alternate characterization to bipartite graphs. So, we will write it as a theorem and we will prove it. A graph is bipartite if and only if it contains no cycles of odd length. Okay. And you look at all the cycles in the graph, if none of those cycles are of odd length, then it will invariably be a bipartite graph. Okay. And if you take a bipartite graph that cannot contain any cycles of odd length. Let us try and prove this theorem. Okay, one direction is easy. Suppose let us just imagine that there is an odd cycle. Suppose this is one particular cycle in the graph, cycle of having odd number of edges. Now, suppose this graph was colorable, then all these vertices would have gotten some color. So, if you take this vertex, one of these vertex, start at any vertex, if you give color 1 to this, its neighbors must surely get a different color. So, this must be of color 2, there is no other option, and the next vertex should be of color 1, and the next should be 2, and the next should again be 1, and that would cause this particular edge to be colored in such a way that both its vertices have the same color. So, that is not a valid coloring. So, this would happen in any odd length cycle. If you have a cycle of odd length, you start at any vertex, by the time you reach back to the vertex, you will see that as the colors have to alternate, the last edge cannot be colored properly. Okay. So, odd length cycles would imply that the graph cannot be colored using two colors, and hence the graph cannot be bipartite. So, we know that odd length cycle implies not bipartite. So, the contrapositive of this statement would mean bipartite implies no odd cycles. Okay. Now, we need to show the other direction, that is, let us take a graph which does not contain any odd cycle, that will be bipartite. Okay. So, let us look at any graph and we are going to color the edges in a particular order. Okay. So, we take any particular vertex, let us call this as V1. So, we are now looking at a graph without any odd cycles and we will show that it is bipartite. Okay. So, let us take any particular vertex of such a graph. So, let G be a graph without odd cycles, okay, and let us choose a particular vertex V1. Okay. We are going to construct an ordering, and for this we will first look at all the vertices which are adjacent to V1. Okay. That is what we will call as level 1. Okay. So, level 1 consists of all vertices which are neighbors of V1, and then we will look at the neighbors of vertices in level 1, okay, that will be your level 2. Okay. Look at all their neighbors except of course the neighbor V1, we will look at all the other neighbors and that we will be putting in the next level, and we continue this. So, we will get something like a leveled arrangement of the vertices. This is the level 0, that is vertex V1, and then there are level 1 vertices, its neighbors will give you the level 2 and so on. So, this will have some number of levels. Note that if you look at the original graph and look at all its edges, they will pass from level I to level I plus 1 or level I to level I minus 1. They cannot jump 2 levels, because if there was some vertex here and there was let us say there was a vertex at level 1 and it is connected to level 3, then automatically it would have been in level 2 as well, because it is a neighbor. So, it would have to be in level 2. So, there is no possibility of jumping the levels. Okay. So, all the neighbors were essentially accounted for here. Of course, the previous neighbors, whatever, I mean, for example, if you take a node here, some of its neighbors are going to be here and then some of the neighbors are going to be in the layer above it. What we have argued is nothing can go from one layer to this is forbidden. Okay. Now, can there be edge between two vertices in the same level? Is this possible? Okay. We will argue that this is also not possible, because suppose there was one such edge that is within a level, then these would have some ancestor, some common ancestor. Of course, V1 is their common ancestor, but there could be some common ancestor at a layer closer to this particular level. Okay, if you call this as level I, there is some other level which is closer to I than, let us say, V1, and there is a node there such that is a common ancestor of both U and V. Okay. Now, if you look at the common ancestor and the path to U, there is a path from that common ancestor to V and the path from the common ancestor to U, and both these paths will have length exactly the height difference between these two layers, and they will be equal. And therefore, if you look at, so if this was a common ancestor, there is a path, common ancestor, and then there is a path to U, there is a path to V, and there is an edge between them. Together, this forms an odd cycle, because this path length is x, this path length is x, and this is of length 1, and therefore 2x plus 1 being an odd number, you have a cycle of odd length. But we assume that G is a graph without odd cycles. We wrote it differently, but Yeah, so this is G is a graph without odd cycles. So if you take a graph without odd cycles, then this is not possible. Okay. So all the edges will be between adjacent layers, and within a layer there are no edges. Now any graph without odd cycle, we can construct this leveled arrangement, and now if you look at the odd layers and give it one color and the even layers and give it another color, we can essentially get a valid coloring using just two color, okay, because between two odd layers the distance is at least 2 and therefore there is no edge between them. Same applies for between the even layers. Okay. So that completes the proof that, I mean, if you take a graph without odd cycles, they can be colored with two colors. It is a two colorable graph or a bipartite graph. Okay. Now we will see another concept called as minimal spanning trees. We learned about trees, and trees were graphs such that there were no cycles in it and that they were connected. Now here when we are talking about minimal spanning tree, we have a specialized kind of graph under consideration. So what we will look at is what are called as weighted graphs. Okay. So weighted graph is nothing but a graph with the edges having a certain weight. So a weighted graph is a graph with weights on the edges. That means we have a function, let us say Wt, which goes from the edge set to natural numbers. Okay. So Wte would be this will be called as the weight of the edge. For example, here is a weighted graph with 6 vertices and the weights being as indicated by the numbers above the edges. Okay. So here if you look at the edge AB and the edge BC, they are having the same weight. Okay. So what we will assume in our study of minimal spanning trees is that the edge weights are distinct. So if E1 is not equal to E2, then weight of E1 is not equal to weight of E2. Okay. So we can think about our weighted graphs as graphs having unique edge weights. Each edge weight is a distinct number and we will assume that it is a natural number. Now let us define what are minimal spanning trees. A spanning tree is a tree. So spanning tree of a graph G is a tree T, which is a subgraph of G. So there are no isolated vertices, there are no isolated components. So if you take a subgraph of G, which means a subset of the edges such that they form a connected graph and it does not have any cycle. In other words, you want a tree such that every vertex is part of this tree. For example, if I take the red colored edges, that forms a spanning tree. You can see that there are many spanning trees for this particular graphs. Now the weight of a spanning tree is defined as the sum of the weights of the edges. So weight of a spanning tree is the sum over the edges in T, weight of edge. Okay. For example, the red tree that has been described, its weight is, so if you call the red tree by T, weight of T is equal to 1 plus 3 plus 2 plus 5 plus 6. So, that is 17. Okay. And minimal spanning tree is a tree which has the smallest weight amongst all the spanning trees. So, there could be multiple spanning trees, and if we did not assume that the edge weights are distinct, there is a possibility that there could be multiple trees with same weight, and so all of them will be valid minimal spanning trees. Look at the smallest weighted tree, spanning tree, that is called as a minimal spanning tree. Okay. For example, in this graph, if you take another collection of edges, so if you take these blue colored edges, their weight is going to be, if you call them as T1, weight of T1 is going to be 1 plus 2 plus 2 plus 4 plus 4, that is going to be 13. Okay. So, that is less than T, but it is not clear why this should be the minimal spanning tree of this particular graph. Now, we will see certain properties which will help us compute the minimal spanning tree of any graph. Okay. So, there are two crucial properties which will help us identify the minimal spanning tree. The first property is called as the cut property. Okay. So, cut property essentially states that the least weighted cut edge is part of every minimal spanning tree. Okay. So, we need to understand what is a cut edge. Okay. So, a cut is defined as a partition of the vertices. So, when we say partition of vertices, we need to get, so we need to have a partition of the vertices into two parts. Okay, and two non-empty parts. So, let us say this is your part A and this is part B. So, A union B is your vertex, collection of vertex set, and the edges. So, now if you look at the edges of the graph, there are three kinds of edges: edges which lie completely inside A, edges which lie completely inside B, and then there are edges which go from A to B. Okay, these are the only three kinds of edges, and these edges which go from one part of the cut to the other part is called as the cut edge. Okay. So, that essentially tells us what is the cut property. Look at all these edges, these cut edges, for any possible cut, all such edges would essentially be part of every minimal spanning tree. Here we are assuming that the edge weights are distinct, and therefore, there will be a unique least weighted cut edge. We can always relax these conditions. For example, if there are multiple edges carrying the same weight, even then we can apply cut property. For that, what we need to guarantee is that for the cut that we have chosen, there is a least weighted cut edge. I mean, there is one cut edge whose weight is strictly less than every other one, and that cut edge would be present in everything else. If you had multiple cut edges, minimal ones all having the same weight, then what we can do, I mean, at best is that one of those would be part of every minimal spanning tree. Okay, so let us look at some particular uses of the above lemma. So, if you look at the cut where vertex A is on one side. So, if vertex A is on one side and everything else is on the other side, okay, and there are two edges which goes from this side to the other side, namely the edge having weight 1 and the edge having weight 2. The cut property says that 1 must surely be present in all minimal spanning trees. Why is this so? We will see shortly. Similarly, if we had taken A and B as a cut, as one side of the cut and rest everything on the other side, or ABD on one side and CEF on the other side, then there are two cut edges, namely the edge 4 and the edge 5, sorry, the edge having weight 4 and the edge having weight 2, and we can say that the edge BC will surely be part of every minimal spanning tree. Now, let us see how we can prove cut property. Now, suppose the cut property is false, what does it mean? That means there is some particular edge which is the least weighted cut edge, but is still not present in the minimal spanning tree. Okay. So, suppose let us say the edge E is equal to u comma v is the minimum weighted cut edge, okay, across, let us say the cut we will call it as A comma B cut. It means one side is A and the other side is B, and A, let us say A contains U and B contains V, okay. That is how UV is a cut edge. And suppose E does not belong to MST. So, let us just draw the MST. So, some tree is there, and then if you add this edge E into it, what will happen is that is going to create a cycle, okay, because the spanning tree, by virtue of this being a spanning tree, there is already a path between U and V, okay, because every vertex was present and this is the tree. Okay. Now, if you add the edge UV, that is going to create a cycle. Now, can we somehow say that the minimal spanning tree that you currently have is not the optimal spanning tree? So, this diagram was our spanning tree T, and we are assuming that UV is the minimum weighted cut edge. Now, minimum weighted cut edge means it is across some particular cut A comma B, and we want to identify those vertices. So, let us first draw the diagram. So, this is our A and this is our B, and on top of this diagram we are going to lay out our tree. So, tree will have some edges on the A side, some edges on the B side, and surely because it is a tree there are going to be edges going from one side to the other. Okay. Now, what we are guaranteed by our assumptions is that UV is not one of the edges. but if you add uv to this, that is going to create a cycle. Okay. So, let us just add the edge uv. So, suppose u is this and v is this, we add uv to this, that is going to create a cycle, and in this cycle, by virtue of this being a cycle, there is a, I mean if you just trace the edges, there is a path from v to u. Okay. U to v is an edge that we had added, and surely there is a path from v to u, and that path should surely cross the cut at some point. Okay. That means there is an edge which starts in B and ends up in A. By virtue of that being a cut edge for the cut AB, its weight, so let us call this as E prime, weight of E prime is going to be greater than weight of E. So, now let us imagine the tree which is obtained by removing the edge E prime. So, this edge we are throwing out, and we are in place of that adding the uv edge. Now, we will claim that the new object is going to be a tree. It is going to be a tree because this does not contain any cycle. The only cycle that was there was the cycle that we got by adding uv. Now, that cycle has been destroyed by removing the edge E prime. So, this is a cycle free graph, and every vertex which is connected earlier still remains connected. So, this is a new tree and the weight of this particular tree. So, let us say the new tree is T prime, weight of T prime is equal to weight of T plus weight of uv minus weight of E prime, but E prime's weight is going to be greater than the weight of uv or the edge E, and therefore, this quantity is a negative quantity. So, weight of T plus a negative quantity will give you the weight of T prime, and this contradicts the assumption that T was the tree having least weight. So, it is not a minimal spanning. This argument tells us that T cannot be the minimal spanning tree, okay, because we have found one particular tree whose weight is strictly less than that of T. Okay. So, that is the proof of cut property. Okay. So, construct any possible cut, split the vertices into any possible manner, and look at the edges which goes from one side of the cut to the other, and amongst those the least weighted edge surely is going to be present in all minimal spanning trees. That is the cut property. Okay. Later on we will see how we can repeatedly use this cut property and construct the minimal spanning tree of any graph. Okay. The next property which is again going to be a useful property for constructing minimal spanning tree is the cycle property. Okay. So, consider a cycle in any graph, any weighted graph, and look at the maximum weighted edge in that cycle. Make a guess as to whether that edge will be present or absent in minimal spanning trees. Okay. So, cycle property states that max weighted edge will not be part of any minimal spanning tree. Okay. So, how do we prove this? Let us take a graph G and suppose the cycle property is false. Okay. And before we go into the proof, let us see a couple of examples. So, in this particular diagram, in this graph G, if we look at dB, that is the maximum weighted edge of the cycle involving edges with weight 1, 2 and 3. So, the edge marked in green cannot be present. This edge cannot be present because it is a maximum weighted edge. The same applies to the edge EC, because that is also the maximum weighted edge of the cycle BCED, and EF is also not part of a minimal spanning tree or part of any minimal spanning tree, because that is the maximum weighted edge of the cycle CFE. Okay. So, in this diagram, in this graph, if you look at the edges that has been excluded, they are fit to be excluded. None of those edges can be part of any minimal spanning tree, and therefore, if you look at the remaining edges, they must be part of every minimal spanning tree. Okay. Reason being, if you remove any one of them, there is no other edge that you can add to make this graph connected. So, this tree indicated by the blue lines are going to be the unique minimal spanning tree. So, now let us see why cycle property is true. Let us see a proof of cycle property. So, suppose cycle property is false, what does it mean? That means there exists a cycle such that E is the maximum weight edge of that cycle and E belongs to the minimal spanning tree. Let us call the minimal spanning tree as T. So, E belongs to T. E is an edge of the tree T. Okay. This should give us a contradiction. So, let us look at our tree, we will draw it out. Okay. And some particular edge E, which is the maximum weighted edge of some particular cycle, is present. Okay. Suppose this was that particular edge. If you remove that particular edge, the tree will automatically break into two parts. Okay. So, that is going to naturally give us a cut involving or a partition of the vertices. So, let us say we are going to draw our tree like this. This is our edge UV, and there are no other edge going from side A to side B in the tree. So, there are all these other vertices, they are all connected to U, and there are all these other vertices which are connected to V. So, that is our tree. Our minimal spanning tree was something of this kind, and if you remove UV, then that disconnects the graph. But now, if you think of the original cycle C, of which UV was the maximum edge, if you look at that cycle and trace out that cycle starting at the edge UV, then at some point there should be an edge going back into, going from B to A. Okay. The cycle of which the edge E was part of must have an edge which goes from B to A. Okay. And clearly this is not going to be an edge that was part of the tree T, because the tree T did not have any edge going from side A to side B other than the UV edge. Okay. So, let us call this edge as E prime, okay, and since this is part of the cycle, weight of E prime is going to be strictly less than weight of UV. Again, replacing the edge E prime, replacing the edge E with E prime, we get a tree of strictly less weight. Okay. So, we can conclude that T is not the minimal spanning tree. Okay. And therefore, our assumption is contradicted. Okay. So, we know that cycle property is also true. So, now equipped with these two properties, cycle property and cut property, we will describe a couple of algorithms to solve the minimal spanning tree problem. Okay. The minimal spanning tree problem is you are given some particular graph, some particular weighted graph, and you need to compute the minimal spanning tree. Okay. And these are classic algorithms. The first algorithm is called as Kruskal's algorithm. We won't bother about the data structures used in these algorithms, but instead we will just look at the steps of the algorithm. Okay. So, Kruskal's algorithm does the following: you look at all the edges sorted by their weights in increasing order. Okay. So, consider edges in increasing order of their weights. Okay, so E1, E2 and so on. If there were m edges, then you look at edges E1, E2, Em and keep on adding this into the tree. Okay, so initially you have these n vertices which we can think of as isolated vertices, and first edge that you add is E1 and then maybe you will add E2 and so on. Each time you are adding an edge, you will check if there is a cycle formed by the edges that are already present. Okay. So, suppose E1, E2 and then you added E3 and suppose E4 was between these, then you are not going to add E4. Okay. So, consider the edges in these orders, keep adding them without creating cycles. Okay. And in the end, if you had started with a connected graph, you will get the minimal spanning tree. Okay. Why is this algorithm correct? Okay. The reason is the cycle property. Now, every edge that we have removed from this particular tree is an edge which deserved to be removed, because that cannot be part of any minimal spanning tree. This also tells us that if the edge weights were distinct, that gives rise to unique ordering on the edges, and therefore it will create a unique minimal spanning tree. Okay. So, on graphs where the edge weights are distinct, there is precisely one minimal spanning tree, and that can be found by this method. Method's correctness rests on the fact that all the edges that we have removed in the process to create the tree those are the edges which cannot be present in any minimal spanning tree. Okay, so, if we look at our original graph, okay, so if we sorted the edges according to the edge weights, the edge weights would have been 1, 2, 2, 3, 4, 4, 5, 6. Okay, we need to have some way of identifying which was the weight 2 edge. Okay. But if you look at weight 1 and 2, these edges will automatically be added. This also can be added. When you add 3, there is a cycle, so that is not going to be added. When you add 4, that is not going to create a cycle, that gets added. The next 4 is also going to be added, and 5 and 6 are going to create cycles. Okay, and therefore they will not be added, and therefore this example verified that the tree obtained is indeed the minimal spanning tree. Now, Prim's algorithm is also a very simple way of constructing the minimal spanning tree. Okay. So, you start at the algorithm works in the following way: you start at one particular vertex and look at all its neighbors, and amongst the neighbors add the least weighted edge. Okay, and keep on, and then let us say if you have added one particular vertex, now you consider this as a set, and from this collection find out the least weighted edge and then add that, and then consider those 3 as a set and add the least weighted edge, and so on. Okay. So, at any stage you have a collection of edges, collection of vertices which forms a connected component, and from this component look at the least weighted outgoing edge, and that is going to be added to expand this particular tree, and in the end you will get a tree, and that tree is guaranteed to be the minimal spanning tree. Why is it the minimal spanning tree? Because each edge that you add at any given stage is the minimum weighted edge of a certain cut. So, when you added the first edge, if you look at the cut consisting of just that one vertex and everything else on the other side, okay, you have a valid reason for adding the particular edge that you have added. At any particular stage you have some partial tree, and those partial trees define a set of vertices, and the complement of that would be the other part. So, if you consider this as a cut AB, the next edge that you are going to add is the minimum weighted edge across the cut AB, and therefore by cut property that is an edge which deserves to be added to every minimal spanning tree. Okay. So, we have learned 2 algorithms to compute the minimal spanning tree, and the correctness of both these algorithms comes from simple properties, simple graph properties like cut property and cycle property. We'll stop here for today's we'll end today's lecture here. We'll continue studying other properties of graphs in the coming lectures.